Hi, it's good to see you're still doing physics. Well done, you. Right, let's go through the answers, page 61 to 63. 61 and 62 are the compulsory ones, and I think I'll probably do a separate video for 63. As always, make sure you attempt them yourself. I keep talking about this idea of hypercorrection effect. It's actually shown in science that if you want to learn more, you attempt it first, even if it means you get it wrong. And then you go back and you see the answers and fix them, as opposed to just watching me do them correctly the first time. Here we go, force diagram of someone hanging on a rope bridge. So what's going on in my head? Remember that a while ago I had a thing that said, do they have a constant velocity or are they accelerating? That means no net force, and that means there is a net force. They've got a constant velocity here, they've got a constant velocity of 0. It looks like they're just hanging there. So there's no net force. That goes on in my head the whole time as I'm making these. Okay, force diagram, obviously. Oh, my system is the person. I like when I draw the systems because I can see the things that are going into the system, and that kind of gives away what my forces are going to be. With what contact's been made with the system, what's my contact forces. I always tend to draw gravity first because it's the one that's always there unless we're in deep space somewhere. Let's say it's a lady by Earth. Now there's effectively it's one rope here, but the way we look at this is we think there's sort of two ropes pulling out from each side. So there's a tension force this way on lady by rope, and there's a tension force this way. Because I can see the rope coming into the system here, and I can see the rope coming into the system here. So that's why I think of it as two ropes pulling outwards. On lady by rope. Are any of these the same size? Well, it's the same rope, so I can at least say that those are the same size. I'm not sure about gravity. Let's draw our vector addition diagram. What do you want to start with? Doesn't matter. They'll all be the same answer. Let's do it two ways, and just to show you. I'm going to draw this one first. Then I'm going to draw gravity next. It's meant to be straight down, but a bit wonky. And there's my other tension force. Great. Ends back where I started. No net force. What if I drawn this one first, and then gravity, and then this one? Same answer. Great. This is a squirrel, could be a cat, no one's sure. One of the great questions in life. Maybe it's a badger. We don't really have those animals in New Zealand. It's got a thick tail. Maybe it's a beaver. Not sure. Anyway, it's sitting still on a roof. That's the main thing. So first thing I know, net force equals 0. That stays in my head as I'm doing all this. Force gravity on, what are we calling it? A squirrel. I'll go with that. Squirrel by Earth. I gave you this clue a couple of videos back in the notes, is that the normal force always acts 90 degrees. Normal is always 90 degrees to a surface. So here's the surface here, so the normal force has to come up like this. Normal on squirrel by roof. I'm going to leave it there because I don't know what else there is. I'm going to show you that you can move back and forth between this vector addition diagram and the force diagram. I know the net force has to be 0. So as I draw my vector addition diagram, I draw my first one, I'm going to go with gravity. I draw my next one head to tail. Normal. I want to get back here because I know that the net force is 0. So I need to have another arrow that kind of goes up the slope. Something that goes parallel to the slope. Oh, I know something that goes parallel to the slope. Friction. And when you think about it, if this is a slippery roof, he wouldn't be able to sit there. There needs to be some friction holding him up the slope a little bit. On squirrel by roof. Now this one is a bit tough to get your head around, but you'll see a couple of versions of this, and this is something they do like asking every other year in the exam. So this is certainly something you have to be able to do. Right. Are any of these the same size? Not necessarily. I know, and this is only from experience, and from what it looks like in the diagram here, the normal force is smaller than gravity. Yeah. So I couldn't put any equality marks on any of them. There's a force diagram for a skier who slides with negligible friction. It's the same question, kind of. There's something on a slope, but now there's negligible, which means no, or means so small you can ignore it. That means you can ignore the friction force. Label the force vector. So if there's no friction force, and I can't think of any other forces than what was on my squirrel there's nothing different about this situation, except for the friction, I think he must be accelerating. So that means my vector addition diagram shows it's not a closed diagram. It doesn't end up where it started from. Force gravity on skier by Earth. Here's my surface, so 90 degrees. Force normal on skier by, you could say, snow or slope or whatever you want to call it. Right, let's put these together. Oh, that is a good straight down arrow. Quite pleased with that. FG and then head to tail FN. Now remember, if it doesn't finish where it started from, you go to the start, draw a dotted double arrow down there, and that's your total. Let's think about that arrow. That says the total force is going down the slope. That's the way they're accelerating. That makes sense. Child on a swing has been pulled back before being released. System. When you do the system, it's easy to see the things that are entering the system to be applying forces. There's this rope. There's this person pulling back in this direction. So I've got my, stop at you, got my force of gravity on child by Earth. I've got my one tension force up here. On child by, what do you want to call that, the rope of the swing or chain, and then there's the person's holding as well. Tension, because it's a pulling force. All pulling forces are tensions. On child by parent. They're being pulled back before being released. I'm just going to make this simpler and say that they're being held there. So their velocity is 0. So that their net force is 0. Let me clarify that. Their velocity is 0 and they're being held there. So not just that their velocity is 0, but their velocity is 0 for a long time. Held there. Which mainly means their acceleration is 0. Because remember when we did the that hockey ball being thrown up and then coming down? When it gets to the top, you can have velocity equals 0 for an instant, but acceleration wasn't equal to 0. That's a different situation. This one here, they're being held here. They're being held in place, I think, and that means their velocity, their forces balanced. Right, put these forces together. downwards. I always start with downwards. You don't need to though. You can start with anything. Let's go this way next. Let's do the rope comes up here. F tension, and the other rope comes up here. Good. We're back where we started from. Great. Last one, I think, before we get on to the extension question. A climber who's stopped to rest. So net force equals 0. On a slope, we know that the normal force is up here somewhere. And if we draw our, it's just so much easier when you draw your system. You can see the ropes entering the system, the ground's entering the system. For me, it kind of just makes it easier. On climber by earth, there's a tension force up this way. F tension on climber by rope, and there's the normal force up this way, always 90 degrees to the surface on climber by ground. Put them together. I always put the gravity first. Let's do another one. Let's go this one first. And I'm going to do gravity. Let's label them F normal, F gravity, F tension. I think that's it for the normal questions. Cool. They were hard, but you get better at them. And if we keep practicing them in our little quizzes to start with, you will get them.